Hello everyone, my name is Kirill Nekludov and today I'll tell you about our paper Wasserstein Quantum Monte Carlo. I would like to start with the problem statement and motivation. In this paper we want to solve the stationary Schrödinger equation, which is given the potential V of x, we want to find the eigenfunction psi of x, which corresponds to the minimal eigenvalue E, which is energy. And the conventional approach to this problem is the energy minimization. That is, we want to minimize E of Q, where Q of x is the coordinate density given by the squared absolute value of psi of x. And we estimate it as the expectation over Q of x of the local energy, which is given by this formula. So to estimate the energy, we have to have access to samples and the density. And this seemingly simple formulation actually has a lot of mathematical and computational challenges. In this paper, we would like to show the gradient flows perspective. That is, we consider this problem as an optimization problem, and we want to derive a gradient flow which minimizes the energy. We can informally say that we just want to perform the gradient descent. That is that next distribution we can get simply as the previous one, where we subtract the gradient of the energy functional. Formally, we can say that the next distribution is defined by the minimizing movement scheme. That is, it minimizes the energy, and also it minimizes some notion of proximity to the previous distribution, where the notion of proximity here is the KL divergence. Once we take the limit of dt going to 0, we arrive at the following partial differential equation. This partial differential equation describes the evolution of the density, minimizing the energy functional. However, I would like to show you some intuition. How does it happen? Let's say we have some model in orange, model density in orange, and we minimize some distance to the target density in blue, following this partial differential equation. And this is what's going to happen. First, the model fits to the nearest Gaussian, but then it teleports probability mass to another Gaussian. Okay, so what if we introduce a different notion of closeness? Namely, we'll use Wasserstein 2 distance. Before we used this minimizing movement scheme with the KL divergence, and now we can swap the KL divergence with the Wasserstein 2 distance, and we'll get another gradient flow. We'll get it once again as taking the limit of dt going to 0, and we'll arrive at a different PDE. This partial differential equation is a continuity equation. However, to show you the intuition behind it, once again, I want to show you just an animation. That is, we start with the same model, with the same model density in orange and the same target density in blue, and we minimize the same distance between them. This time, something different is happening, because now we see that there is no case of probability mass teleportation. Instead, this PDE transports probability mass. First, it transports it to the nearest Gaussian and then to another Gaussian. So far, so good. But how do we simulate these gradient flows in practice? So it's quite straightforward. We consider that our current density Qt lies in some parametric manifold, parameterized with some parameters theta. Then we can predict the next density at time t plus delta t using, let's say, Euler scheme. And we can project this density back to the parametric manifold, having some other now parametric density q of theta plus delta theta. And of course, for different gradient flows, we have different dynamics on the parametric manifold. So let's take a look on what's going to happen in practice. This is one iteration of quantum variational Monte Carlo, which is the classical variational Monte Carlo algorithm for estimating the ground state. And it looks as follows. We start with some parametric density q of x theta. Then we collect samples from this density using Markov chain Monte Carlo algorithms. And then we update our parameters as follows. First, we evaluate the local energy. Then we evaluate the parameter update. And then we just update our parameters with some learning rate. Of course, these three steps is the projection onto the parametric family, onto our parametric manifold. And once we get new parameters theta prime, we will update our samples using Markov chain Monte Carlo algorithms to sample from the new model of the density, q of x theta prime. In this paper, we propose a different gradient flow and a different update of the parameters. So the only second step changes. Here it is. So we propose essentially a different objective for variational Monte Carlo, which incorporates this transportation property that I've shown you before. Let's go to the experimental results. For energy minimization on different electronic systems for different molecules, we observe that our algorithm converges as fast or faster than the baseline. However, low energy values doesn't necessarily indicate the convergence to the ground state, the minimal eigenstate. To assess the convergence, we estimate the variance of the local energy, because the ground state, for the ground state, the local energy is constant, thus the variance has to be zero. And we see that once again, our algorithm in most cases outperforms baselines in terms of this convergence. As long as this local energy constant, the gradient of the local energy has to be zero, thus its norm has to be zero. And here we see that, like, in all cases, our algorithms converge faster to zero gradient of the local energy. To summarize, we consider different gradient flows with different notion of proximity, the KL divergence and Wasserstein to distance. These different notions of proximity result in different partial differential equations, minimizing the energy. One teleports mass, as I've shown you before, and another actually transports samples along this vector field. And we believe this is beneficial for the Markov chain Monte Carlo step, because it's easier to update samples once we change the density by transporting mass. You'll find much more details in the paper. Fisher-Rao gradient flow is actually the imaginary time evolution of the Schrödinger equation. You'll find different metrics, interpolation between metrics, and more details about derivations, codes, experiment details, and that's it. Thank you for your attention.